I am going to introduce a course on extremes. Do you know that extremes are crucial in engineering design and that we cannot design an engineering work without the knowledge of the extremes? Do you know that the behavior of random extremes is very different from the case of mean or regular values? Do you want to know how to deal with extremes and other related values? If your answer is positive, you are invited to discover extremes and how to deal with them. It is clear that extremes appear in natural calamities and disasters. For example, tsunamis, as you can see in the picture. This is what happened after a tsunami in January in 2005 in Indonesia. This is the flood that occurred in India in the Kosi River. However, the extremes appear also in real life. This is an example of a collapse of a bridge in Minneapolis, and the cause of this is that we have extreme values in loads maxima or in strength minima. Look, the problem with loads is when they are very large, when they are very extremely large, and the problem with strength is when they are very low. So we have problems with maxima and minima. Both are extremes. Normally, when we have a disaster, it's because there is a combination of several causes, not only one. And this is because we use safety factors and we use some considerations that improve the situation of the structures when there is a problem. This is another example of a railway line in which we have a slope collapse. In order to understand what extremes are, we need to understand the concept of order statistics. Assume that you have a sample of the last n years and you have registered the maximum temperatures in a given site. And you have x1, x2, xn. They are random, so this is a random variable. You can consider the sample and sort the values in increasing order of magnitude from the minimum to the maximum. And then you can look to the earth position. The statistics of order R is the value that occupies the earth position. Of course, the first is the minimum, the last one is the maximum. But all the order statistics are an n-dimensional random variable. So we are in front of a random variable that results after sorting the initial sample. And we can be interested in the distribution function of all these variables, or these order statistic variables. And to do that, we can use a correspondence between the order statistics and the multinomial experiments. And we will be able to obtain a closed formula that you have there, and that formula gives you the joint density of any subset of k order statistics. It is a powerful formula because it includes only one order statistic, any one, couples, or three order statistics, or any number, including all order statistics. So we can use that very interesting formula to obtain and to analyze order statistics. To understand better what order statistics are, let me put you one example. Consider the case of a class in a school with only 5 students. Assume that the grades of the students can be reproduced by a normal density, as you can see there, a normal 0,1 density. And then we take examination and consider the grades obtained by the 5 students and sort the grades. We have the worst student, and then the second worst, the third worst, up to the best student. And the order statistics represent the grades of each of these students. So you can see that the densities move from left to right, from the worst student to the best student. And these densities represents, as you can see, the grades of each student. This is what the order statistics means. Another interesting thing is, assume you have a normal density and you take a sample of size 2, and you obtain the maximum of these two values. Or you take a sample of size 10, and you take the maximum, or the maximum of 100, or 1,000, or 10,000. Then the density will move to the right in the way you can see. There is a displacement to the right, and there is also a change in the scale. However, if we have a Gumbel distribution as the parent, and we consider the maximum of 10, 100, 1,000, etc., we get the displacement to the right, but no change of scale. And if we use a reverse Gumbel, we obtain the other figure. It is very important to see what to do when you want to reproduce maximum values, because they are very important in engineering. We know that the distribution function of a given variable is f of x, and I take a sample of size n. The maximum of n has as distribution function the same f of x, but raised to the nth power. But this is good when I know the cumulative distribution function f. But what happens if I don't know the distribution function of the parent? That I cannot use the formula. So it is very interesting to see what happens in the limit when n goes to infinity, if I can obtain good approximations for the true distribution of the maxima, or the true distribution of the minima in case we are interested in the minima. Then there is a very interesting theorem that says that given any parent distribution, any distribution, the limit distribution possible when n goes to infinity, all of them belong to a single family, which is the generalized string value family. This family includes three subfamilies: the Weibull, the Gumbel, and the Frechet families for maxima, or the corresponding for minima. That is very interesting, because when we have to approximate the maximum of a given random variable, we don't need to concern about the distribution function of this variable, because we know that we can be very close for the maximum with the generalized string value, or with the Weibull, Gumbel, or Frechet. So this is a very important result that we need to know. In other words, the maximal Weibull, Gumbel, and Frechet families can be used to approximate the true distribution of maximum coming from any distribution f of x, and the same can be said for minimum. In this course, you will be given interesting tables that gives you for the Weibull, Gumbel, and Frechet for maximum and minimum, the cumulative distribution function, the mean, the median, the mode, the variance, and the quantile. So you will have a very nice information and complete information to work with these distributions. In this plot, I want to show you the Gumbel. The Gumbel distribution is in between Frechet and Weibull. In other words, it separates the two families. This is a plot with Gumbel, Weibull, and Frechet distributions, all with mean 0. And you can see that the thick line, which is the Gumbel, separates both families. And this means that Gumbel can be approximated by Frechet and Weibull as much as possible. So, in really, we could avoid Gumbel distribution and work with Weibull or Frechet, because we can approximate that distribution as close as possible. An interesting question is, if I have a distribution function, cumulative distribution function f of x, how can I know if I should use Weibull, Gumbel, or Frechet? There is a very interesting theorem. It is my theorem, that just obtaining a limit, you can determine the value of a parameter kappa, and if kappa is larger than 0, that distribution can be approximated by Weibull, if it is equal to 0 by Gumbel, and if it is less than 0 by Frechet. So this simple theorem will allow you to know which is the adequate distribution to be used. But even more, because of the theory of extremes, we know that the Weibull distribution is not the limit distribution if the random variable is unlimited. If I have a random variable that can reach values as large as possible, Weibull won't be the distribution, the limit distribution for that variable, will be Frechet. On the contrary, if the distribution is limited on the right high sum, then the Fréchet distribution cannot be the limit distribution. So I can decide between Weibull and Fréchet only knowing the range of the random variable we are looking for, we are working with. Because Gumbel can be approximated by Fréchet or by Weibull, we can always decide immediately only knowing the range of the random variable. In the course, you will be given some tables that gives you the limit distribution for maxima and for minima of the most well-known distribution, as normal, exponential, log normal, gamma, Weibull, Pareto, Cauchy, etc. An interesting tool to work with extreme is the case of probability papers. Probability papers are papers that are designed changing the scales of the probability and the random variable in such a way that any distribution function plotted on that paper is a straight line. If it is a straight line, that distribution function belongs to the family. If it is not, it does not belong to the family. So we can plot a sample. If the trend is more or less a straight line, we can say this comes from this family. If the trend is not a straight line, we can say this sample doesn't come from the family. And then we will be informed of how to build these probability papers. You will be given a table like that in which you can see the changes you need to perform in the probability scale and in the random variable scale to obtain the normal, the log normal, the Weibull, Gumbel and Fréchet papers for maxima and minima. You will be given this information to work with these probability papers. However, it is very important to know that because the Weibull, Gumbel and Fréchet are only limiting distributions, I have to use only the tail to feed the data. It is an error. It shouldn't be done to include all the data points. We need only to take a sample and to take the largest sample for the case of maxima and the smallest values for the case of minima, and then you need to fit the data in a Gumbel probability paper. Just looking to the curvature on the right hand side or in the left hand side, you can decide which is the right or the adequate extreme value distribution. If you have a straight line trend, the right distribution is Gumbel. If you have a positive curvature, then you should use Weibull. If you have a negative curvature, you should use the Fréchet. We also consider the limit distribution of order statistics, not only for the extremes. And in this case, we need to differentiate between central order statistics and high and low order statistics. The central order statistics can be approximated by normal distributions, and the high and low order statistics give a more complicated limit distribution that will be given to you by formulas that relate to the extreme values. We will also consider the case of distributions, of limit distributions in the case of dependence. Up to now, we have considered the case of independence, and what happened when we have dependence. The question is, do we have the same limit distributions as in the previous case? Under what conditions the previous limit distribution still are valid distributions? These are very important questions that we answer. And normally I can tell you in summary that if the dependence is not very strong, is weak, then the distribution functions will correspond to the same distribution, limit distributions, that in the case of independence. On the other, if that is not the case, then you get different distribution, and we will give you some examples. And we will also consider the case of exceedances. Exceedances are very important because are values that exceed a given threshold, are above a given threshold. And then in the case of extremes, we can ignore what is below. It is very interesting to observe the past and have observation on the past and to see what will happen in the future. And then we will give formulas that provide the expected number of exceedances of a given value for the future. There is a very important theorem that is due to Pickens, Jr., which is the following. If you have a random variable and you consider the values above a threshold, the exceedances over a threshold, then if this threshold value is large enough, the distribution of this new variable is generalized Pareto. And this is a very nice solution to analyze extremes, because if we work only with maxima, we are ignoring a very important piece of information that is given by those values that are very high but not are maxima, but are close to the maxima. With the case of the exceedances, we analyze not maxima, only we analyze all data which are above a given threshold value, and this is much better than using only the maxima. We need to be concerned about the return period. When we have a very high value of, for example, a very high temperature, a very high speed wind, or very high wave, we want to know how long will it take for that level to be repeated in the future. And we call return period to the mean time that expresses the repetition of these high values. We can calculate the return periods just by using the cumulative distribution function of the yearly maxima very easily. And finally, I want to introduce an example. This is the example of fabric water, in which I want to reproduce a three-dimensional random variable, which is the Hs mass, the H mass, and the T mass, which represent the maximum wave height, the significant wave height, and also the period. I have to build a three-dimensional random variable, but instead of defining the joint density, I am going to do it in the following way. First, I am going to define the marginal distribution of the maximum, of the significant wave height maximum. Next, I am going to define the conditional distribution of the maximum given the previous one. And finally, I am going to define the conditional distribution of the period given the two previous ones. And to this end, because I have to consider first the marginal density of the significant wave height, what I do is that I use the generalized Pareto distributions, because I know that they have been considered only wave heights larger than 3 meters. So in some way there is a consideration of the exceedances of 3 meters. And then I try to use the generalized Pareto, and then I use some PP and QQ plots that gives you a very good idea of the fitting. And because the fit is good enough, I decide that it is a generalized Pareto distribution. To decide what is the conditional distribution of H mass given the significant wave height, I plot the data, and I see there a linear regression, and then I take the residuals, and I see that they follow a reverse Weibull distribution, and then I choose that model, a linear regression with Weibull distribution conditionals. And finally, I have to define the conditional distribution of the period given the other two. I plot the data, and I see that there is a very nice linear regression. I see the residual of the plot of the residuals, and I test that, and I see that they are normal, so I get a very nice conditional normal. Okay, this is the end of my summary about this course. You have seen that order statistics, what they are, and that the minimum and the maximum are two important particular cases. You already know that the generalized stream value stream distribution permits approximation maxima and minima of any parent population, and that the generalized Pareto distribution allows us to work with exceedances and shortfalls. You also know that probability papers are useful for analyzing extremes and that return periods are important and easily obtainable. If you think that this material is important to your work, you are invited to learn and enjoy following this free course.